So today we will be learning some advanced topics for Python programming that are relevant if you're going to be doing high performance computing. Uh, so ACES is a high performance computing cluster. So that is a perfect example of a environment where you would need to know how to do uh, relevant Python things for that environment. So today we're going to be doing a number of things. Pretty early, we're going to be logging into ACES. We're going to be talking about some different concepts that are relevant for Python. There are many ways to get software. Modules is one. We're going to be getting into the Jupyter notebook so we can start testing our software environments. Then we're going to try some other ways to get software that are appropriate for a high-performance computing environment. We have the virtual environment and the Conda environment and the container, which are all ways that you can install your own Python packages. You do not need to ask an administrator to install Python packages. If we don't already have what you need, you can install it yourself. Later, we'll be dipping our toes in the water for some high performance computing algorithm strategies. So not installing software, but actually trying to do computations. We're going to be discussing how to do parallelism, so taking advantage of the multiple cores within a node, and checkpointing, which is working around the constraint of having to share the node with other people, and you may run out of time. So checkpointing is how you can continue after you resume working after an interruption. So who's ready to log into the ACES cluster? Yay! So we make our cluster available in your browser using um, a framework called Open on Demand. So the web page where you access our cluster is called the ACES portal. You can navigate to the ACES portal from our homepage using the drop-down menu, or you can follow the link, which I will just drop into the Zoom chat. So that's the link to our ACES portal. ACES, because ACES is authenticated through the Access authentication system, when you attempt to access the portal, it will redirect you to the Access CI logon. There's more than one way to use the Access CI logon. If you select your identity provider, you can just provide a password, or you can select your institution, in which case it redirects you again to your institution, and you can log in using your favorite method. I actually prefer to log in using my institution, which is Texas A&M. So I only have one browser token that I need to worry about, which is my Texas A&M Central Authentication Service browser token. And then Access can reuse that token, and then ACES can reuse that token. So it's very convenient. But by hook or by crook, you somehow need to authenticate yourself to Access, and then you will hopefully be redirected back to the ACES portal, or you can just click the link again. And you'll see our homepage for the ACES portal, which has the message of the day and a number of tabs in a menu at the top. So for today's instruction and exercises, we're going to be mostly using the clusters menu and the interactive apps menu. Let's do the first of our exercises. So in order to explore the ACES cluster, we will be using shell access from time to time. And so you can open a shell terminal on the login node. There are 3 login nodes. You get one at random. And you use the menu and it opens in a new tab. So you can see on my screen, I click it clusters ACES shell access and I get a new tab. The new tab opens and there's like a bug that I don't quite understand, where if I increase my font size so that you can read it, then it starts acting weird. So hopefully that doesn't become too much of a problem today. So the first concept we're going to learn is modules. Modules are our local way of sharing pre-installed software to you. Every site has their own way of doing this, but the module system is a common choice. So let's take a look at the module system. So we have LMOD, which is one of several possible module systems. And the module system is controlled by an executable named module. Each software is bundled into packages or collections of packages called modules. And so each module has a name and a version. There are several kinds of modules, and they are organized hierarchically. So at the bottom of the hierarchy, you have the toolchain modules, which are bundles of compiler software mainly. So for example, one toolchain is GCC, the new compiler collection, and it has versions. Another toolchain might be OpenMPI, which is closely related, but has additional libraries for doing parallel processing. And so the next layer of hierarchy above that would be software that depends on compilers. So for example, PyTorch, which is Python software, but it also depends on some packages which have been compiled in C. So when you need access to PyTorch, then implicitly you also need access to the toolchain that matches. Some of the versions of the modules don't look like numbers. For example, this PyTorch module has a PyTorch numeric version, but also it is concatenated with a CUDA version. And that is because CUDA is not part of the tool chain, so it is an additional degree of freedom when you compile the module, which version of CUDA you'll plug into it. So that means for a given version of PyTorch and a given toolchain, you also have to specify a version of CUDA. Once you have selected your modules, the point of the command, the module command, is that it will set all of the environment variables so that your shell knows how to find these specific executables and their libraries. We have entire short courses dedicated to just understanding the module system. You can take a look on our YouTube channel and our knowledge base. But for today, we're going to be focusing on just a small subset of what's possible. So the main, when you're learning to use the module system, the first thing you need to do is explore what modules are available. So there's two module commands that are commonly used. Module avail lists all the available modules, and you can search for modules, but the search is case sensitive. So if you don't know exactly what you're looking for, then you may have trouble finding it. The other search tool that's more maybe more intelligent is the module spider, which does not only search the names of the modules, but it can also search their descriptions. So if you match a word that's in the description, then the module will be found. So if you're not exactly sure what the module is named, but you know what its description is, then Module Spider can help you find it. Additionally, Module Spider can give you more information about a specific module. So once you have determined the module name, you can type in Module Spider and then the module name, and if you include the version as well, you can get more detailed information about even that specific version of that module. So we will, once you have determined which module and version you're interested in, then we can use the module commands to manipulate your shell environment variables. Module load sets environment variables so that all the software in the specified packages gets added to your shell variables, and your shell will be able to use those. Module list tells you which modules you already loaded, and module purge does the opposite. It sets your shell back to the unmodified environment. So how about an exercise? Your exercise is to discover versions of Python that are already installed and try to load one into your environment variables so that you can use it. Allow me to clarify one fact. Python is installed in the system root directories on every node of ACES. So if you go to any node and type Python 3, you will get an interpreter. But I wonder if this works. No, I don't know what I'm doing. Okay. But so its version is quite old. 3.6.8 is from a few years ago. So allow me to just specify the system Python that's installed in USR bin Python on every node is old. We would prefer not to use it. Probably all of your scientific software depends on a newer version of Python. So you should really avoid using the system Python. Therefore, you're interested in searching for modules that provide newer versions of Python. So module avail, or MLA for short, Python, module avail Python, MLA Python. Okay, so I think the problem is that MLA Python has cached all of these, and the other one says, I can't do that right now. Okay, so MLA Python worked better for me this time. So there are many things. Some of these are not Python. BioPython is not Python. Those are additional libraries. So you have to scroll till you find actual Python. Here it is. So these are the Python modules that are currently available to me. So I can see how many there are. There are quite a few, and pretty much all of them, except for this 2.7, pretty much all of them are newer than what's the system Python. So we should pick one of these down near the bottom. The short course is going to pick one that we can consistently use throughout the day, so we don't have to keep switching around. I think it's one of these. Yes. So your task is to load Python 3.11.3. So if you try to module load Python 3.11.3, it's going to say, no, you can't do that. And the reason you can't do that is because the modules are organized hierarchically, and so you are required to load the tool chains along with the software. You cannot load only the software. And the reason you have to explicitly load tool chains is because there may be multiple builds of software that have the same version that are only distinguished from each other because they have a different tool chain. So if you do not specify the tool chain, you have not uniquely specified the software. So you need to discover what is the correct tool chain to load. And the way to do that is by using module spider followed by the full module name with its version. And that will give you all the information you need to understand how to load this module. So the output of module spider gives you the description, and then it gives you a hint. You will need to load all the modules on any one of the lines below before the Python 3.11.3 module is available to load. There's only one line here, so this is the only choice. You have to do this combination of tool chains, and there's only one tool chain here. So you just make a note of it, and you need to do that as well because I did not put the answer in the slide, but you can select it and use your normal browser copy and paste hotkeys. So now we know that we need to do module load, toolchain, and Python. So if you specify that you want this toolchain and this Python, then you have uniquely specified the software. So this does not produce an error. How do we confirm that it worked? We need to do module list. So ML list for short. I don't really like typing ML for some reason. So I type module list, and I can see that I now have a stack of software. And the bottom of the stack in position 1 is GCC core. And at the top of the stack is Python 3.11.3. And in the middle, there is a whole bunch of other related dependencies. So you might ask, Richard, if Python depends on all of these things, why did I only have to specify one tool chain? And that is because we have tried to make the tool chains, we try to limit the number of tool chains, and we try to have all of the related software depend on the same tool chain, so that when you specify that you want Python, if you specify the tool chain, then for each of these other modules, there will be exactly one possibility for a version of this module that is compatible with Python and the tool chain. So you don't have to specify a version of bzip2 because there's only one bzip2 that's compatible with both Python 3 and GCC Core 12. So if we build our stack in such a way that the hierarchy is wide, but then quickly narrows to a bunch of very narrow branches, then you can go quite far down a branch before you reach a point of ambiguity. So for the majority of softwares, you'll only have to specify one or two tool chains, which are those critical points on the branch where you have to make a decision. We have a question in the Zoom chat. Chin asks, do we need to load this Python every time we start a new shell access? If you are using Python and you're using the shell in your browser, then yes, you'll have to execute your module command each time you log in. One way that I like to simplify that is to actually write down the module command in a file. So if I was going to be doing this again, I would do echo that command into env.sh, for example, is my favorite name for it. And then if I shut down my terminal and get a new one, then I don't have to remember what that module command is because I know that I saved it in env.sh, so I just have to remember to source env.sh, and I have my modules back. So that's my favorite way of making the resilience problem less annoying. I hope I have been able to answer your question. And again, the only thing that env.sh is it's literally just the module command, but I put it in a file so I don't have to remember it. Okay, so after you know how to load Python 3, what happens if we take away the toolchain? So you can only have one version of a given software loaded at any time because two would conflict. So if we module load GCC core 13 make sure I get the right number, 13.2.0, then you get a warning that says, we have had to make some changes to your environment. And that is because when you take away, when you add something that conflicts with what you already had, it disables what you already had, and then it disables everything that depended on that. And it will try to reload as much as it can. So there is a bzip2 that's compatible with GCC core 13. And so for some of these, it was able to replace them, but it wasn't able to replace Python 3.11.3 because Python 3.11.3 is not compatible with GCC core 13.2.0. It is only compatible with GCC core 12.3.0. So once you take away the toolchain, it has to take away the software as well. So now I no longer have access to Python 3.11.3. So I'm going to put it back the way it was. So it's reactivated Python because I have my toolchain back. So if I do Python 3 dash dash version, it's now Python 3.11.3. And where is it located? It's not at the operating system root, but it in fact is in our software partition, which is shared on all the nodes. So you can do this procedure on any node. Vardil is asking, is this setup specific to ACES? Yes. So many clusters have a module system. They tend to work in similar ways. So the general concept of execute this command to set your environment, that you will see over and over again. But executing this specific command with this combination of Python version, that is specific to ACES. If you go to a different cluster, they will name their Python modules differently, and they will have a different, perhaps a different set of tool chains that you are required to load, or maybe there's no requirement for loading tool chains on that particular cluster. So the details about what goes in the commands will vary from cluster to cluster, but most clusters will have some kind of commands that you run in order to use the pre-installed software. If you were using your laptop, probably you don't have a module system because you would not be expected to install multiple versions of software because you just would want the one that you want. Module systems are primarily used when you need to share the cluster with multiple users, and they all have different needs. So let's return to the slide. The slide says we've done all these steps, so we can now learn how to clean up our environment. So if I have loaded modules and I do module purge, then I no longer have any modules loaded, and which Python 3 again returns the system Python. So are there any I've answered some questions. Are there any more questions about the module system, which is the pre-installed software on ACES? It's already available. So that's what that is. For the rest of the course, we're going to be focusing on installing your own Python packages. That's weird. Zoom says there's a thumbs up, but I don't see it. Where could it be? And it's gone. Okay, that was a bug. Ryan asks, are there specific modules which are incompatible with the ACES cluster? So the example that comes to mind would be CUDA, because CUDA is a software that is used to build GPU-ready applications, and it is highly dependent on the hardware that you have. So for a given hardware, you need to match that hardware to the version of CUDA. So it is possible that you might want to use a version of CUDA that corresponds to a hardware that we don't have on ACES. Or you might use a version of CUDA that doesn't work with the hardware that we do have on ACES. So being cognizant of the hardware sometimes is a relevant limitation for the software versions as well. But usually, most softwares will work on most clusters. I suppose another example would be proprietary licensed software. We don't tend to keep a lot of licensed software on ACES because it's hard to get a license for proprietary software for a cluster that is shared by literally the whole nation. So if you're wanting to use proprietary software, it's more likely you're going to use a cluster that has a more restrictive participation. So the clusters that we have at A&M that are just for A&M members, those we can get licenses for proprietary software. There are other Python version installed. You typed UV Python list. I'm not familiar with what happens when you type UV Python list on the login nodes. I don't know if UV is saying these Pythons are already available, or if it is saying that it can install them. I'm very new to UV myself. There are lots of versions of Python, but I don't know how to find them the way UV finds them. Ryan asks, will this training be transferable to the Grace or faster? Yes, it will be very transferable. We set up our module systems almost exactly the same on all our clusters. The module versions will vary slightly, but the commands will have the same command words. So once you understand the concept of what is a toolchain module, then you will understand how to load modules on any of the Texas A&M HPRC clusters. Okay, believe I have answered enough questions about modules that I have a desire to move forward. So I'm going to teach the next topic now, which is Jupyter Notebook. Jupyter Notebook is quite simply a very basic IDE for Python, and we're going to be using it to just explore what Python can do in various environments. So I have provided a interactive app called Jupyter Notebook for Python training, which is a simplified version of the regular Jupyter Notebook app. So I've taken away the options you don't need to worry about and pre-setting up your workspace so that you have the files you need to do the exercises. So I need everyone who is able to log into ACES to return to the ACES portal and find the Jupyter Notebook for Python training, that one specifically, not the Jupyter Notebook general purpose application. If you click Jupyter Notebook for Python training, then you get a simpler form with fewer options to click on, and it will set up your training directory so that you have all the files you need to do the exercises. So there are many environments that are possible to use with Jupyter Notebook. That's the point of why we're using this IDE to explore them. And for the first example, we're going to be using the Python module plus virtual env option. We're not using the virtual env yet. It is an option, and we're going to choose no for that option. So the first variant of Jupyter Notebook is going to be Python module plus virtual env, and the module will be Python 3.11.3, which is the same version that we were exploring on the command line. And the virtual env option will be blank. So we're not using that option right now. So that will be your first combination of parameters. You have a field for the number of cores, and I've set it to 4. You can go down to 1, I think, if you don't want 4 cores for some reason. But I reserved enough cores for this short course that we can all have 4 without worrying about running out. And 4 should be enough to demonstrate all the functions we're trying to understand. Because you're on the training allocation, there's not really a particular reason why you need to worry about that. So you can just leave it at 4. So you click launch, and it creates a job. The job will go through a sequence of states. You have the queued state, the starting state, which takes about 2 minutes. Jupyter is not a fast software. And then the running state. When the job is in the running state, it is now a web server that you can connect to that will present the IDE as a tab in your browser. So I have my job in the running state. It landed on node AC009. You can click the connect to Jupyter, and it will open the Jupyter IDE in a tab. So the Jupyter IDE has 2 main front pages, 2 main pages. You have the file navigator page, and then if you open an IPython notebook, then you have the notebook editor page. And those will be in separate tabs usually. Sorry, I clicked ahead a little bit. So here we have the environment test notebook. If you have successfully launched your Jupyter notebook server and connected to it, please confirm that you have a copy of the environment test notebook, because that's what we're going to be using for most of these exercises. So the environment test notebooks it includes a number of simple commands to just check which Python libraries are available to you in your current environment. So the first cell of the notebook has import sys, print sys executable, and sys version. Anybody here seen Jupyter IDE before? Are you familiar with this? Can you give a thumbs in the Zoom if you have used Jupyter or Google Colab or even IPython notebooks in VS Code are very similar. So the point is that you select a cell and then you click the run button to execute the code in that cell. So the output of this cell this time was we're using Python 3.11, which is what we requested from the drop-down menu, so that makes sense. And it has the same path that we saw on the command line when we did this on the command line, which means under the hood, the server did the module load command before giving you your Python kernel. If you're interested in these other cells, what they do is they show you various modules that we may be interested in at some point today. So NumPy is the numeric Python, and it comes bundled with this particular version because you did not select a virtual environment. The default environment is, well, we assume you don't want literally no packages, so we'll just give you a bundle of commonly used packages. So that includes NumPy, and that is the default for the interactive app. So if we go back to the interactive apps, if you read carefully, it says if you provide a virtual env, it will override the default Jupyter. So when you want Jupyter Notebook, it depends on Python, but it's not going to be just Python. You need a variety of things to run a successful IDE. So we have a default available, and you can override the default by providing a virtual env. So we'll be exploring that in due time. So we have a default IPython kernel, and at a later time, you'll be installing your own IPython kernels. So if you wanted to understand more about the environment test, you don't only have to do this in Jupyter. These are just regular Python commands. And you may have noticed that in the same workspace, there's also environment test.py, which is just the same Python commands, but instead of a notebook, it's a regular script file. So we can navigate to where that is located. We could go cd scratch training, today's date, and there are the files. And you can execute the environment test script. So for example, if I'm using the system Python and I execute the environment test script, it reports that it is version 3.6. There is a NumPy. There's not an IPython kernel. So the system Python cannot run Jupyter notebooks. If you start doing your module load commands, let's see if I still have any module load commands. I do have one. So if I execute those module load commands, And then if I use the Python 3 that's coming from Python 3.11 to execute the environment test script, now I get that Python 3.11 is the one that I'm using, and NumPy was not found because this particular Python 3, if you don't load anything else, it's kind of naked. It doesn't have anything. Well, so where does NumPy come from? It comes from that SciPy module. We got a hint of that SciPy module here. So we can use Module Spider to explore this and determine if we can load that. Yes, you can load that. So module load SciPy bundle says I did not do it right. Oh, because the tool chain is slightly different. It doesn't have the word core. Sometimes I forget that if you load GCC core, then you also have to load GCC, which for some reason is a separate tool chain. What did I do? Oh, I forgot to provide the load command. Now we can load SciPy bundle, and now we can execute our test script, and now we can find NumPy. So this is the same NumPy that we saw in the Jupyter IDE. So what I'm doing is I'm showing you that what the Jupyter IDE does is the same as what we do on the command line. You load some modules, and then you execute these regular Python commands. So Dimitrios is asking a question. When we run the Jupyter notebook, is it on the login node? No, the Jupyter notebook is going to be on a compute node. So if you go to the My Interactive Sessions tab, which is just the two squares, for some reason it doesn't have a title. So the two squares icon takes you to your My Interactive Sessions tab, and it will tell you which node each job is running on. So this Jupyter notebook, which I have open here, is running on node AC09. Whereas this session is happening on ACES login 3. So those are different nodes. Ryan asks, when deciding on how many cores to use. It is not always easy to know how many cores to use. Python is generally a single-threaded application. So for general purpose, like just writing some commands and testing them, one core is enough. But since we're doing HPC, I assume you're interested in multi-core. So you would request as many cores as you intend to use simultaneously. There are up to, I think, 96 cores on a node on ACES. But it's unlikely that your Python application will use that many cores because Python is not the most efficient for multi-core applications. If we're loading modules while running our processes on a CPU node, so Dimitrios is asking about using cores on the CPU node. So, I'm sorry, on the login node. So on the login node, I did not specify a number of cores. And in fact, all of the cores on the login node are available to my shell, but we have rules. You're not supposed to use all the cores on the login node because the login nodes are for sharing. So if you actually try to use all the cores, then we will kick your shell off the login node so that you don't become a problem for the other users. The only things I've done on the login node is run very small Python scripts that are single-threaded, so I was only using one core, so it's not a problem. Once you know you're going to be using more than one core, you should not be on the login node. That's when you need to be on a compute node. So this Jupyter notebook here would be a perfectly acceptable place to run multi-core because it is on a compute node. And when you're on a compute node, you have to explicitly set the maximum number of cores your job will use. So that is how you know that you're sharing correctly with other people. Demetrios asks, you know what? I misunderstood Demetrios's question. He was actually asking if you load modules on the login node and then you run on the compute node, yes, you have to load your modules again. So, for example, uh, Jupyter can Jupyter can run notebooks. Jupyter Lab can also run a shell. This is not Jupyter Lab. Yeah. So it's hard for me to show you. I could, if you get a shell on a compute node, which is possible, and we'll do it later, then you will have to re-execute your module commands. You have to execute them on each shell. So if it's a new shell, then you need your modules again. Now, if you execute there are specific commands that can move your shell from one node to another, but it's not a new shell, then sometimes you get to keep your modules. But to be safe, I like to reload them anyway, just in case. Are we supposed to be learning something? Oh, yeah, I was supposed to do this exercise. So I did the wrong exercise. I apologize. Um, we were supposed to load a different version of SciPy and then check for NumPy. If you want to do the version that's in the slides, then you can. So if we go to the same web page that you used to register, you will see that there is now ACES Python Fall 2025 PDF, and you can click on it to open it in your browser, and it's the same slides. So you can scroll down to where we are and copy and paste the commands. So I could copy this command out of here and paste it into my shell and swap out my modules for some different modules. How about that? It is now time for us to move on to the next topic in high performance computing, and that is virtual environments. So the default behavior of a package manager, such as the system package managers or the Python package managers, is to install packages in the global root directory so that everyone can use them. But you do not have permission to install packages into the global root directory of a shared file system if you are not the administrator. So you need to be able to specify that you would like to install your packages somewhere else. The basic recommended way to do that in Python is called a virtual environment, which sets up a more or less alternative installation area at a location of your choosing. And then you can install packages there and use them at will. It becomes kind of like your own module that you build for yourself. So, what kinds of packages are you likely to want to install? We have seen some examples already. We've seen NumPy. We've seen Jupyter Notebook. We do know that you can get these from the module system, which are the pre-installed software. But if you're installing your own software, then mixing and matching the pre-installed software with your own software doesn't always work. So you may just have to install your own copies of these as well. So the virtual environment is a file structure that holds a specific Python version and package dependencies. So there's a base Python installation, which you will get from the module system, for example. But that doesn't mean you have to install your packages in the same location where base Python is installed. You can install your packages in a separate location. You can also have multiple virtual environments, each of which correspond to potentially a different base Python, so that you can switch from one to another without losing your previous environments. So it's common to have a virtual environment for each project. So on the ACES cluster, we have a tool which is create VN, and it will help you to build virtual environments. So in order to build a virtual environment, you need to decide what the base Python will be. The create VN tool cannot give you a default base Python. You need to select one from the module system. That is to say, the create VN tool was specifically designed to work with the module system. So instead of installing Python from scratch, you pick one from the module system, and the create VN will build a virtual environment that is designed to work with the version of Python that you have selected from the module system. If you do not want to use the create VN tool, of course, the Python package virtual environment can also build virtual environments, but there will be some extra steps to make it work with the module system that we have. It's not particularly difficult, they're just extra steps. So if you, let's do the exercise. So you need to be on a login node. Oh no, my connection was terminated. I'll have to get a new connection. Going to leave. So if you actually close the Jupyter window, it's fine. The server doesn't stop running. You can reopen the window. I'm just closing it because I had a lot of tabs and I wanted to make some space for myself. So I'm opening a new shell session. I landed on login 3. And we need to do some of these exercises. So we're going to load our Python version. Oh, that's the same one I did earlier. So I get to repeat my previous command. Source env.sh. Module list. Nice. Save myself a few keystrokes there. So now that we have selected a version of Python from the module system, the create VN tool will set up a virtual environment that uses the Python from the module system as its base Python, but will give you a space in the Scratch directory to install packages. Create _ venv, and you give it a name. So I'm going to name it training env today's date because I want to remember why I did this when I come back later. I'll go, oh, I don't need that anymore. So I'm creating an environment and it says, oh, you're not allowed to have special characters. Whoopsies. Dots. Do dots count? Wow, really no dots? Okay. So the create venv tool will not allow me to put special characters in the venv name. That's not a general restriction of virtual environments. It's specific to this tool. So now it says I have created a virtual environment, and if you create the virtual environment with the create venv tool, then you can set the virtual environment using the activate venv tool. Oh, underscores. Okay. My coworker points out that I probably should have been using underscores. That's fine. It's just an example. So now I created a virtual environment. If I do which Python 3, I still see the Python from the base Python, but I can lose that at any time. Oh no, I lost my modules. My my base Python is missing. How do I make sure that when I'm using my environment, I'm using the correct base Python? Well, when you have a virtual environment, it's important that you load packages that match the base Python that they were installed for. So you can either do it manually, you can always reload your modules and then activate your environment, but because we're using the HPRC specific create venv tool, those two steps are bundled together. So we can use the activate venv tool and provide the name of, what did I name it? Training env 2025-1202. There we go. It said, and then it gives a warning. And now if I check for which Python 3, oh, that's not right. Oh, it's because I didn't do the right command. I typed activate venv. It's actually supposed to be source activate venv. There we go. So you'll notice that my prompt has changed. Now my prompt has been prepended with the name of the environment, and that is to remind you that currently my shell has the correct commands to use this environment for installing packages. So if I install any packages right now, they will land in this environment rather than, for example, in the root of the file system. So how are we all doing? Has everyone been able to load some Python, create an env, and then source activate the env and see that your prompt changes? So now that your prompt is different, you can use your favorite package managers like pip and I think maybe even UV, although UV you'll have to be maybe more specific because UV is going to want to create its own virtual environment. You have to tell it not to do that. Uh, but yeah, you can use your favorite package managers to install Python packages, and now they will land in the correct directory. So if I navigate to the Scratch directory, to the training directory, and I execute the environment test script, I can see that I have Python, but I don't have NumPy, I don't have Dask. Oh, for sure, never use sudo on a shared cluster. You are not the administrator. You should not be trying to use sudo. If you're even trying to use sudo, you've probably already made a mistake. Uh, yes, where was I? Ah, yes. So I have a virtual environment, but it does not contain Dask, and I would like it to contain Dask. So I just need to use my favorite package manager. In this case, I'm using pip install Dask, and it says found some stuff, put some stuff. Okay, where did it go? Now, if we execute our environment test again, it says, oh, this time I did find Dask. And where did I find it? In the Scratch user virtual environment named training env. That's what I named mine. You can name yours whatever you want. And there it installed it. So now you know how to install a Python package into your Scratch space. Why is that important? Because on a shared cluster, file systems have limitations. So if we go over to the dashboard, this is just a sidebar. If you go to the dashboard, you will see that you have virtual env management. That's fun. You will see that you have quota information. So every partition in a shared file system will have a quota. And my quota in home is smaller and my quota in Scratch is larger. So I would prefer to install things in Scratch. Uh, is that clear to everyone why we're talking about this? I kind of got lost in my head. Okay, so we've actually finished this exercise, if you're following along, which is install Dask, check that we've installed Dask, and now we have to deactivate the environment. So if we deactivate the environment, the prompt prefix goes away. So now if I was to try to do pip, it would say it would not install in the virtual environment. It would do something wrong. So I will not do it. Do not use pip unless you have a known place where it will install. Otherwise, it's going to do something you don't want, for sure. There's more than one thing it might do, but they're all things you don't want it to do. Okay, were there any questions about this procedure? Let's have a question from Richard. If you're not on an HPRC system and you don't have create venv, how would you do this procedure? Yes, I can show you how to do it the other way. So if we navigate to that virtual envs directory, if we navigate to anywhere, for example, here, you can create a venv by using the Python 3, the venv module, which is which I believe to be installed in this. Let's see, do I still have my yes, I still have those. So that's Python 3.11. And I believe Python 3.11 includes a venv module. So if we use the venv module, we can create a new training venv. And now we have a new training venv in a current directory. And you can do source new training venv bin activate, which is similar to the other command. And now we've prefixed the shell prompt. So now I could do pip install Dask, and Dask should go into that environment. And then I can deactivate. So how is that different? The main difference is if you use the Python built-in, you have to specify the path and you have to manually load your modules. That's the difference. Otherwise, the procedure is the same. So what the HPRC specific tool is giving you is it will find your environment. You don't have to give the full path to it, and it will load your modules for you. That's the difference. Otherwise, you have to load the modules on your own. If you module purge, if you module purge and then activate the regular environment the regular way, then it's actually broken. What will happen is if you try to use the libraries, it will say something is missing. I know I need GCC, but I can't find it because I never loaded GCC. The virtual environment can find the Python, but it can't find all of its dependencies. That's what the module system is giving you, is it's giving you all of Python's dependencies. So as soon as you try to do anything with it, it's going to be like, the libraries don't exist. What's going on here? Uh, and so we have finished with this activity. And I forgot what's coming next. I'm sharing my screen, right? Right? Okay. For some reason, I was like, oh no, did I forget to share my screen? Have I been talking to the void for 20 minutes? Okay. Um, so we will be doing some activities later that will require some packages. So while you're here, it would be convenient if you wanted to do these extra setup steps. So from a fresh terminal, I'm on a fresh terminal now. As you can see, I have no modules. I have the system Python. I can now do activate venv, training env, whatever I named it, 2025-1202. Ah, darn it, I forgot. It's source activate venv. And my prompt has been changed, and I have my modules. So it conveniently knows how to load those modules back, so your environment is always correct. That is the helpful hint. Now that I have my prefix, it is safe to do module installation. So I'm going to install some things that I need for the exercise later. Pip install, what do I need? I already did Dask, right? So I need notebook, NumPy, Joblib, Dask, IPy, Cytoscape. Notebook, NumPy, Joblib, Dask, IPy, Cytoscape. And it'll probably say that Dask was already satisfied, so it'll just skip that. Installing a bunch of stuff. Installing a bunch of stuff. That's a bunch of stuff. Okay, bunch of packages. And this step, IPy kernel install, what it does is it makes it so that when you're running a Jupyter notebook, you can switch from one environment to the other by clicking a button. Um, Otherwise, you have to stop the job and restart a new job with the new base environment. But if you don't want to restart a job from a new base environment, this can allow you to switch from one environment to the other without stopping your job in the middle. You just have to register each environment you want to be able to switch to using this tool. Python 3 M IPY kernel install IPY kernel install user. So not for everyone, but just for me. And you can give it whatever name you want. Training kernel. So installed kernel spec training kernel in my home directory. It's a tiny file that just says there is an environment somewhere and this is how you get to it. Is that clear enough? And deactivate list venvs just for completeness. So I have a training env. Yep, it's there. I would like to move forward with the learning and show everyone what we can do with our virtual environment now that we have created it. So let's go back to the interactive sessions. Now I'm actually going to stop my Jupyter notebook because I don't need it anymore. So there's two ways to stop it. If you delete it from here, it's like an error technically. You forcibly kill it. If you don't want to be so brutal, you can also tell the notebook to shut itself down. So we have the um, apparently I don't know how to shut down a Jupyter notebook. I really thought there was a way. Well, apparently there's no button to shut down this notebook. So I guess we're going to have to use the delete button here. Goodbye. So if I delete the session, it's the same thing as shutting it down. It does it in a very violent way. Okay, so we need to, because if we all have our multiple jobs, we might run out of cores. So if you're not using your jobs, you can shut them down. So the exercise that we're going to do next is to use the virtual environment that we created instead of the default one. So we go back to the Jupyter Notebook for Python training form, and you're going to select again Python module plus virtual env. You select again Python 3.11.3, that's the one we're using. But this time you can type in your virtual env. And it does have to be a full path, but you can include shell variables if the shell variables are like always present. So scratch is an always present shell variable. Every shell always has a scratch. So that takes you through to past your username. And if you recall from being on the command line, uh, when you create a virtual environment using the create venv tool, it places it in a directory named virtual_envs. So you can type in the field scratch virtual_envs slash whatever you named it. I named mine training env 2025-1202. If you did not use the create venv tool, that doesn't matter. You can still type the full path to wherever you actually created that virtual environment. So for example, oh, sorry, I made a slight mistake. You do not type in the path to the directory. You type in the name to the path to the activate script. So every virtual environment has a bin activate, and that's the one you need to type in. So for example, it could be virtual envs, the name of your env, bin activate. We also have a default, a backup copy of this located in your training directory. So when you created your training directory, you also got a copy of a training environment. So ls scratch training, today's date, you'll see that there is a training venv. That's a backup. If your venv is not working, you can switch to this one. So it would be scratch training today hyphen today's date training hyphen venv. That's your backup option. This date on my slide is wrong. Sorry about that. So is everybody able to get to this page and type in some kind of valid path to bin activate? You can launch. Please do launch because we need to test the environment to make sure that we understand what it does. So I can connect to Jupyter. I can open my environment test IPyNB. And now I can run these cells. But you see, when I run these cells, I get a different result. Now I still get Python 3.11.3, but now it says Python 3.11.3, but I'm running out of my virtual environment. And I have NumPy installed in my virtual environment, and Dask and IPyKernel because I installed all of those with pip. So it finds them. That's important. So now that we know how to start a Jupyter notebook using the training form, is that the only way to start a Jupyter notebook? No, there's more than one way to start a Jupyter notebook. We also have something called a Drona Composer. The Drona Composer has the same tools that the command line does. So the create venv tool, the activate venv tool. So if you don't want to go to the login node to run those executables, you can do it from our graphical interface called Drona Composer. So let's take a peek at Drona Composer. It's under the Jobs menu. So you go to Drona Composer, and you can start a job. Does it have to be an IPython notebook? No, it could just be a general Python script. So if you just want to execute a general Python script, for example, we have an environment test.py. That's a perfectly valid script, right? Let's execute environment test.py using the environment we created, but using this graphical interface instead of going to the command line. So you can say, I'm going to do a Python environment, and it's going to be one of my private virtual environments. And then you can pick from a list, and it says, yes, I see that Richard, I see you do have a virtual environment that was created with the create venv tool. And then you can pick your Python script. So I can use the file navigator tool to find where I put it. Why are they not sorted by alphabetical? That's so weird. Am I ever going to find it? I'm going to have to type it in by hand. Wow. Oh, there it is. Okay, I found it. So scratch user, your username, the training directory, and then environment test.py. That's the one I would like to launch. And then you can pick your job requirements. So you don't have to worry too much about these right now because we're just doing a quick test. But in theory, you should pick some kind of options. But this quick test doesn't require hardly any resources. So I just picked like something. Expected runtime, 1 minute. And then you have to choose a project account. I have multiple project accounts. So the project account for this course, let me just quickly double check on that, is the one that ends in 53. So I'll pick the one that ends in 53. Okay. And then you can preview, and it says this would be the batch script to do that. It would be source activate training env. Oh yeah, that's what I did on the command line. Then navigate to a directory and then activate that script. All right. We can say, oh, and it requires a job name. Forgot it requires a job name. It's env test for training. Okay. And then it says there's no such file or directory? Oh, because I put a space in the job name. All right, don't put a space in the job name. That's a bug. We should probably correct that bug. That's actually not even a hard bug to correct. You just put some quotes on it. Okay, so it said it completed. So it submitted the batch job. So now we can look at the job submission history and I was expecting to see a refresh button. I guess I have to refresh the page. So I have my job submission history, and here's the job, and it ran. And so I can go to where it ran and see the output. Okay, so here's the output. So it says that it found my Python, it found my NumPy, my Dask, and my IPy kernel. Excellent. So that's just a quick demo for you about our tool that will allow you to run your scripts with a graphical interface instead of from the command line. And now it is 12:06 p.m. So we've been active for some time. We've done a few things. I want to know if there are any questions before I move on. Yes. So the Drona Composer helps you construct your job script from pieces, including pieces that have to do with the environment. So if you know you have an environment, but you don't want to type it in, maybe it's hard to remember how to type it in, then Drona Composer will help you get the correct syntax so that you know that your job script will have the environment. You can also do it manually. So if you're familiar with job scripts, if we go back to where I was using the Drona Composer, so this job, um, this job, the Drona Composer wrote a job script for me, but it's just a normal job script. Once you know how to read it, you can just look at it and say, "Oh, I understand what this is." You could write this job script yourself and submit it with SBatch and get essentially the same result. So Drona Composer put this together for me, but it made it out of pieces that I already understand, so I could have written the script myself. So once you are comfortable with how your Python environment works, then whether or not you use the Drona Composer, I guess is just your preference. But it's very convenient for something like this training session because you can click through a few buttons and know that you haven't missed anything. Everything will be in its proper place. Were there any more questions about either running the virtual environment in Jupyter or running the script using Drona? And I sort of turned them into an exercise but you can do the exercise or you can just say, I'm ready to learn the next way to install Python software. We learned virtual environments. Let's learn a closely related concept called Conda environments. So virtual environments give you a place to put your packages, but they don't give you a package manager. You're just using the default Python package manager. What if you want a different package manager? Well, there is a package manager called Conda, which has access to a wide variety of packages, even some that the Python package manager pip does not have access to. So if you want to use one of those packages that pip cannot install for you, you may have to switch to a different package manager. Conda is a package manager that can install a wider variety of packages than pip can install. In order to use Conda Package Manager, you will need to have a Conda environment. Conda environments are very similar to virtual environments. The basic idea is that it's a place on disk where you will install packages. The upside of Conda is that it has a wider variety of packages that it can install. The downside is it is not fast. It is not efficient. Anaconda was designed for use on a personal desktop. It was not designed for use on a shared cluster. So if you don't have to use Anaconda, you should not use Anaconda. But sometimes you do have to use it because sometimes the package you want is only available through Anaconda. So let's learn how to use it. If you want to use an Conda environment, you have to load a base Conda module. So Conda modules are released essentially like every year, and that gives each time there's a wider and wider variety of packages. It keeps growing. So if I'm on a terminal and I have some modules, yep. Okay, I want to get rid of my modules. And now we can search for Anaconda. Are there any Anaconda on ACES? Yes, we have these. So like roughly once or twice a year, there will be a new release. And the latest one we have on ACES is from last year. So I guess we didn't update that this year, but that's okay. It's good enough. So you find the module you're interested in. Let's learn about it. Module Spider Anaconda 2024-02-1. And it says it blah, blah, blah. And it says this module can be loaded directly. So it does not have a tool chain. That is a benefit of Anaconda, is because it's a package manager that can install a lot of things. It can also install its own dependencies. So if you have Anaconda, it doesn't have to depend on anything. It can be standalone. And that is why when you load Anaconda, you do not have to load any tool chains. So module load Anaconda, just like that. And now we have Anaconda. So if I do which Conda, it says, oh, here it is. It's in the software partition under Anaconda 3. So now I have a Conda, and I can do Conda things. So one of the first things you should do is configure your shell. Now, most of the instructions will tell you to configure your shell to always start Conda automatically every time you log in. And while that can be convenient, it can also be really irritating, because if you decide to work with some software that's outside of Conda, but your Conda is always loading itself when you log in, then now you have like software conflicts in your environment. So we want to prevent unnecessary software conflicts by telling Conda we do not want you to automatically load every shell. So we have the Conda config set auto activate base to false. Conda config set, wait, what was the command again? -- set space auto activate base false. Is that with a capital F? Right, because it's Python false. So now Conda will not try to load itself every time you log in. So it's just a normal module now. You load it when you want to. Now you can create environments. Conda chooses the location for you. You just pick a name. Conda create -n is I would like to choose a name. And you can name it what you want. Conda, I wonder if I already have any. Oh, that's not what I meant to do. Conda envs list. No, I don't know what I'm doing. Conda env list. There we go. Okay, so there is a base environment that comes from the software itself, and I don't have any personal environments. So I need to create one for myself. Conda create -n training 2025 1202. And it says, I'm going to fetch stuff and I'm going to put it here. And then you have a chance to abort, but it looks fine to me, so I'm going to say yes. So now we have a Conda space, and you can activate your space using Conda activate training, but Conda activate only works if you have your Conda shell already loading itself when you log in. I don't like to do that, so this is not going to work consistently. When you log in, this doesn't work until you activate Conda, but if you forget to activate Conda, this won't work. So instead we have the alternative syntax, source activate instead of Conda activate. This is the more generally correct syntax that will work whether or not your shell has already logged in. So it's source activate, and the rest of the syntax is the same, the name of the environment. And now you have prefixed, so it's the same as the virtual environment where you activate it, but with the virtual environment you have to do /bin/activate. With Conda, it's slightly less syntax because Conda is managing the path for you. It knows where the activate script is. You just have to tell it that you want it to do that. So then it prefixes your shell with the prompt. It prefixes your prompt so you know, okay, now my package managers will install here. So that applies to Conda and also pip. So if I do which pip, you can see pip is owned by Anaconda. So if you pip install or Conda install, it will go into the Conda environment. So in a sense, Conda is like a, an extension of the virtual environment. It's virtual environment and more. So let's continue with the activity. Let's install some modules. So we're going to install the same modules we did on the other environment. We need Dask, Notebook, and IPyCytoscape. So for Dask, Conda install Dask. Dask comes out of the standard channel, the default channel, so it knows how to find it. Notebook, there's more than one way to get Notebook, and so the most popular way is through a channel named CondaForge. So we specify a channel when we're ready to install Notebook. So we get the right Notebook, the one we wanted. If you don't specify a channel, but there's more than one option, I don't know what it will do. I assume it will say you didn't specify a channel. Disk quota exceeded. Do you see the disk quota exceeded? That's a thing that commonly happens when you're working with Conda, because Conda is not efficient. It was not designed for a shared cluster where you have a quota. So if you remember earlier, I was checking on my quota. I have a limit to the number of files, and I am at my limit. So I will not be able to do this activity unless I clean something out of my scratch space. If you are using ACES for the first time, then you probably have enough space to do this task. If you're able to do the task, then you can try the environment test script and then Conda deactivate when you're done. We will now proceed to learn the next topic in advanced Python for high performance computing. And that topic will be containers. Containers are a strategy for making software more portable. They can also be used as a strategy for installing software on a shared cluster where you don't have admin privileges to run sudo commands, but you still need to kind of do something like that. So I have an entire course that's literally just about explaining containers. We've already done that this semester. I assume we'll do that again next semester. So I'm going to skip past explaining the theory of containers and let's just get our hands on some containers. So in order to use a container on ACES, we need to get to a compute node because containers are too resource intensive for the login nodes. So we are using srun. That is one way to get to a compute node. There's, of course, multiple ways. We already have a job running on a compute node for Jupyter Notebook Server. We could reuse that. It was perfectly valid. But the syntax that I prepared is for going from scratch in case you want to do this again on another day. It doesn't depend on anything else that's happening. Everybody, so you will need a terminal to run this command. So everybody please go to your cluster's ACES shell access and get a terminal. I landed on login 2. That's important, so we'll take a note of it. Not which login node, but taking a note of which node you're on. We need to just be cognizant of that for this experiment. Okay, so we need to type the srun command. So you can copy and paste out of the PDF. That's probably a clever choice. Srun time equals and some number of minutes, and tasks equals some number of cores. Memory equals some amount of memory and a unit. If you're following along live, you can use the reservation. We have reserved nodes, so we don't have to wait for a node to be available. The PTY says, I would like you to connect the current shell to that compute node, like move the current shell to that compute node. So technically, you get to keep your environment variables. Instead of running a command that's like, instead of just watching from afar, you're going to actually be on that compute node. And then we want to run a shell, and my favorite shell is bash. And if you add the -i flag to bash, it's a little prettier. It's the interactive mode just adds some like it makes your prompt look the way you expect. Otherwise, you don't get the nice prompt. Okay, I think I typed that all in. Let's try it. It says I didn't set an account. That can cause an error. Sometimes you have to set an account. If you need to set an account, then you can use the My Project. So let's talk about no account set. My Project, it'll show you accounts that you have, and you can set one of them as the default. You can see I do have a default, but if you don't have one, you go My Project D, account number, just the number, and that becomes your default. And then you can try the srun again. And that way, I find that to be slightly more convenient than providing the account number as an srun option, which is the basic way to do it, is to provide it as an option. But I prefer to set a default instead. That's just a my preference. Anyways, because it worked for me, you can now see that I am on AC009. I am no longer on the login node. So now I can run my compute heavy tasks and I don't have to worry about hurting any other users because I am on the reserved node. I am not on the shared login node anymore. Um, would you all like to respond in the method of using the Zoom React with the check mark if you are able to use srun or some other method to get to any compute node? You can get to the compute node that you're already running a job on if you know how. You do need a shell if you know how to get a shell on a compute node. Okay, I see some green check marks. That's excellent news. It's working for people. If you need me to remind you um, how that my project works, you execute my project to get the account number, and then you execute my project dash D account number. Some people want to do it that way. Okay, now where was I going? Ah, yes, we were preparing to use a container. So in order to use a container, you need to choose where you're going to download the container to. It becomes a file. So we need to be in an appropriate location. So CD back to your training directory if you need to. It just has to be any directory in the Scratch partition. Should be fine. But I recommend the training directory so you can just erase it when you're done if you want to. Okay, and then the Singularity cache, whenever you're using Singularity to fetch a container, it has a cache as it's pulling down bits and pieces of a large container. And the default location is going to be like in your permanent storage, but this is not a permanent problem. It's a temporary problem. So we should relocate the cache to a temporary directory. TMPDIR is a variable that points to a temporary directory on a compute node. Export singularity underscore cache dir equals $ TMPDIR. Now Singularity will cache the result in a temporary directory so we don't have to worry about cleaning it up later. And finally, we need module load web proxy because containers come from the internet and compute nodes are not connected to the internet by default. You can get to the internet by hopping through our proxy node. And so that's just one extra step to set the environment variables so that Singularity knows that it needs to do it that way. Module load web proxy. So Singularity has a pull command, and the syntax is the target file name, which you get to choose, and then the source, which is somewhere on the internet. Target file name includes the file extension, and there are multiple possible container file formats. I recommend the native Singularity format, which is the SIF. So .sif. It is a compressed file, so it is efficient for space in your Scratch directory. Okay, so the most popular place to get a container is from Docker Hub. And Singularity knows how to pull images from Docker Hub. You just need to use the Docker prefix on your URL. So it's Docker colon and then a URL, // and then, but you actually skip the domain. You don't have to type the Docker Hub domain because that is the default domain when you are pulling from any Docker repository. So we skip typing Docker Hub and we just go straight to the suffix of the website. So I browsed Docker Hub and I found a container repository, Jupyter SciPy notebook, which has releases. We'll just grab the latest. Or you don't have to. This one's actually take a while, by the way. If you actually do this live, this one could take a long time. So normally I don't do this one live. I'll just like start it and then I'll cancel it because it takes too long. But don't worry because I did this in advance so we can all share the notebook. We can all share the container that I made in advance. So even if you don't do this completely, it won't stop you from moving forward. So Singularity is installed. So we can do Singularity pull SciPy notebook latest.sif Docker colon / Jupyter / SciPy notebook -latest. Last time I did this, it ended up taking like over 20 minutes. It's not worth it to do that live, so I'll probably cancel this operation after we talk about it. I'm just letting it run so while we talk about it. So what's happening is the Jupyter community publishes containers with Jupyter software in the container. And this particular bundle of software is Jupyter plus SciPy, which is, all the common scientific Python packages that we love. So by downloading this container, it's kind of like running pip install notebook, pip install SciPy in a virtual environment. But instead of using a package manager to fetch all of the dependencies one at a time, I'm getting all the dependencies at once with a single fetch because the community already assembled that environment. We don't need to reassemble the environment. We can use what's been done. So that's very knowledge efficient. If they can get it right once, we can get it right every time. Okay, so creating SIF file. Last time I did this, it did take a while, so I may cancel it. Any questions about fetching a container, why we're doing this? Let's take a look at my slides. Okay, so the next is after we have downloaded the container image, here's how we test it. I guess I'm bored of waiting for this, so I'll cancel it. Using Control-C to cancel it. Okay, so that's gone. So you can see that the notebook I requested never appeared in my directory because I stopped the process. But we do have this SciPy notebook 2023.sif. I previously downloaded one of these and I keep it around so I can use it as an example. And it's good enough for this example. So you have a link to it in your training directory. It's actually a symbolic link. It points to where I previously downloaded that when I was teaching Singularity in 2023, apparently. So we'll just reuse it. So in order to test Singularity, we need to execute the environment test script, right? So if we execute the environment test script on the compute node, then we get the system Python and we have no packages. So how do we execute the Python that's inside the notebook? Not the system one, sorry, inside the container. So this file is a compressed file. It's got many thousands of files inside, and one of them is a Python executable. So we tell Singularity that we want to use software that's inside there. So Singularity exec is, I'm going to start a executable and it's going to be found inside that container. We can also tell it that we're going to be using files that can be found in the Scratch directory. So that's the B for bind. That I don't know for a fact we need that. Let's try it without that first and see what happens. Singularity exec. I'm skipping the B because I don't think I need it. And we go straight to the name of the container image. That says I want to use software that's in that container image. And then we continue. The next thing you type is going to be what command do you want to run? I want to run Python 3 environment test.py. And it works. So what did it print? It says, well, Python 3 was found, and it was found at opt conda bin Python 3. Is there actually a Python in opt conda bin Python 3? No such file or directory. That path does not exist on the compute node. That path exists inside that compressed file called a container image. And also in the container image, apparently packaged by Conda were all the packages we like. NumPy, Dask, IPyKernel, they were found. Cool. So now we know how to do that from the command line. Can we also do it in Jupyter? Yes. So we return to the interactive app, and we're going to use a different form field this time. We're going to, from the first drop-down menu, type of environment, we have a containers type. So for this one, you type the path to the container image file. I did it this morning to make sure it would work. It did. So I typed Scratch Training SciPy Notebook. That's my symbolic link. Remember, we all have a symbolic link. You could also type the path to the real physical file. It's the same thing. So you type the path to the container image file. Then you can launch your job, and the application knows, okay, I need to find a Jupyter server executable that's located in that container. And it knows how to do it. So we're just waiting for that to start. We click Connect to Jupyter. And we can open up our environment test notebook and execute and run those cells. So we get that Python is found at opt conda bin. NumPy, Dask, and IPyKernel are all installed. But we know these directories don't exist on the compute node. Recall that these jobs run on compute nodes like AC009, which we have established there is no opt conda bin on AC009. So the only way this outcome makes sense is if the Jupyter notebook is in fact using software that is in that container image. Oh, I forgot to click through my slides. So you might choose to throw the reaction in Zoom if you are following along and this is working for you. Click, click, click. That was a generic example I took from another training I did. Containers. Anybody here used a container before? Have you heard of Docker? Docker is a popular container runtime. Some people have heard of Docker before. Do you want to learn more about containers or do you want to learn more about advanced Python for HPC? The next topic we will learn today is parallelism with Joblib and Dask. So Joblib and Dask are two alternative, similar ways to achieve parallel computing with Python. You all feel ready to learn about parallel computing in Python? Exciting. All right. So we'll start by talking about some concepts. We're going to talk about the concepts from the perspective of Dask because Dask is more complex. So if we understand the concepts for Dask, Joblib will be easy. So Dask has concepts called collections. So a collection is a type of a Python object that can store either data or a function. Then there's different ways to organize your data and functions. And you tell Dask how you want your data to flow through your functions, which is called a task graph. So like instead of executing your functions and then having them run now, what you do is you like pretend to execute your functions so that you show Dask the order in which you would like them to be executed. And then Dask takes a note of, okay, execute this one first, then that one, and it builds a task graph. Finally, you can tell Dask, okay, now do that, but like assign lots of different cores to it as much as possible and distribute the work among the cores as much as possible. And so if your graph is just a linear, do A, then B, then C, then Dask won't be able to make it go any faster. But if your graph has parallelism in it, then Dask will detect that and it will assign tasks that don't depend on one another to different cores so they can accelerate. Now, if the cores are all on the same machine, which is what we'll be doing today, then you have some options. I do not use SnakeMake. I have only heard of it. So that is a question you'll have to ask my colleague who has actually used SnakeMake. Dask can also do distributed computation in which the cores are not all on the same node. We won't be demonstrating that today, but it's cool to know that it knows how to do that. So if you're using Dask distributed, then you have multiple layers of orchestration. The client would be the Python executable that you are using to set up your Dask graph. So that's like your Jupyter notebook or something. And then when you tell Dask to run, it launches a separate process called a scheduler. And the scheduler launches separate processes called workers. The scheduler talks to the workers. And when the workers are done, the scheduler reports the result back to the client. Okay, so I have prepared a exercise. So if you previously, way back when I said we will need these packages in order to do the activities. So now is the time we need the packages. So the slideshow suggested naming your environment like myenv. I actually named mine training env, and then so I would use training env, or you can use the container because the container also has the software we need. So you pick one. Actually, I already have the container running, so maybe I'll just continue using the container. If you don't want to use the container, you can go back here and switch over to Python module and type in the name of your environment that you installed all those packages in. So I'm going to shut down my environment test notebook. We're done doing tests. It's time to do some learning. I'm going to shut down my Slurm job on the compute node that I was using to play with Singularity and close that shell. I don't need it right now. So I'm going to start up the Joblib and Dask notebook. Failed to connect. Did I make an error? Oh, I shut down my notebook by mistake. Whoopsies. All right, I guess I'll just make a new one. So I guess I'll go with the Python module, the one that I made today. And definitely you have to select more than one core. You can't do parallelism with only one compute core. That's just Python with extra steps. Okay, so now I have a Jupyter server. I want to open Joblib and Dask. Okay, so now we have a notebook. And before we learn Dask, we're going to learn Joblib, which is similar. It's a little simpler. And then we'll learn Dask. Okay, so I will proceed with talking about Joblib. Definitely remember to execute the import statement. Now oh, there's a typo in the notebook. Whoopsies. So let's do Joblib parallel. So Joblib provides a class named parallel. Its job is to set up worker processes or worker threads. You can make a choice. We'll just go with the default. So parallel is a class, which means we can instantiate the class with one of its keyword arguments. And jobs equals 4. If you recall, when I created the interactive session, I have 4 cores assigned to my job, so I can have 4 workers at the same time. So let's create 4 workers, and that is a parallel class with 4 workers, whatever that means. We're gonna find out. So now what we need to do is we need to assemble some functions into a graph. In order to do that, you don't execute the functions because that's do the work now. I don't want to do the work now. I want to do the work later. So we wrap a function in the delayed to say we're going to do this function, but we're not going to do it now. We're going to do it later. Okay? So if your original function looks like result, you would use it like result equals my function args. Then you construct a delayed function like this. Result delayed equals joblib.delayed, parentheses, my function. So that transforms your function into a delayed function. Then you execute the delayed function by providing the arguments that you would provide to the function. So that's a separate function call. So one function transforms my function into a delayed function. The next function call executes that delayed function, but not right now. Just remember these arguments. And then result is a placeholder for what the result would be if you actually executed the function. So you know that result is not the result of the computation because we haven't done the computation. It's the placeholder for the result of the computation. Okay, so let's say we want to compute the square root. I'll do this in 2 steps. You can do it all in one line, construct your delayed function, and then call your delayed function, but I'm doing it in 2 steps. First, I'm constructing a delayed function. I'm converting the math square root function into a delayed square root. And then I'm going to use the delayed square root function to compute the square root of 4. But of course, I haven't computed the square root of 4. All I've done is I've taken the note. Yes, I need to compute the square root of 4. I'll do it later. So this is, at some later time, compute the square root of 4, but we haven't done it yet. So here's an example of one way that you can use the delayed function to compute to accelerate some computations. So suppose you have a loop. A loop is called embarrassingly parallel if its computations are independent. So we have a for loop. In Python, a for loop will execute sequentially. But we can see here this range function just produces independent integers. You could have done them in any order. So if we run many square roots and append them, then we can have a list of the square roots of the numbers through 10. Well, through 9, because we stop at 10. So the square root of 0 is 0, the square root of 9 is 3. You could have computed the square roots in any order as long as you remember to put them into the correct position in the list. Because the square root of 9 and the square root of 4 are independent computations. So how do we turn this into a graph for Joblib? Step 1 is rewrite the for loop as a list comprehension. So instead of 4x in range, it's now list, and then computation for x in range. I will show you that it's the same. If you print it, you get the same result. So this is just that, but instead of a for loop, we're using a list comprehension. The next step is, instead of computing the square roots now, use the delayed square root. Remember earlier I constructed the delayed square root function? Its job is to remember what to do, but don't do it now. So now we're going to have an array of compute the square root of 1, compute the square root of all the way up to 9. And we'll put them together into that list. So now instead of 0, we have later I will compute the square root of 0. And instead of 3, I have later I will compute the square root of 9. And each one has its proper place in the list. And now we have a list of work to do, essentially. You know what we can do with a list of work to do? We can feed it to our workers. Remember workers? A long time ago, I created workers. That's a parallel class with 4 workers. So workers can accept a list of work to do. You give it to them and they do all the work and they give you the result. How about that, right? So I did it in many steps with print statements so that you could see. but you didn't need those print statements. You could do it all on one line. So it could be joblib parallel, jobs equals 4, execute list comprehension, joblib delayed, math square root x for x in range 10. And then close all those parentheses. And boom, there's 0 through 3. But instead of computing sequentially, they computed in any order up to 4 running at the same time. Pretty cool. So you're having an exercise. If you don't mind doing an exercise after I've been talking at you for 20 minutes. Everybody sick of Richard talking at you for 20 minutes? Let's do an exercise. Create a parallel loop that searches a list of words and counts the number of characters in each word, and then finally report the biggest number of characters that was found. Okay, so Trevor, thank you for sharing your solution. Did anybody well, did anybody do anything other than counting the letters in the words? Because if you chose to do something else, I'm curious to know what you chose to do. You might challenge me to do something. Would anyone like to challenge me to do a parallel loop of embarrassing calculations? That could be fun. So let's go new cell, make it a markdown cell, challenge. Richard tries to solve a student suggested problem. New cell. Somebody got to give me a suggested problem. Number of vowels in each word. Okay. So let's have a string. Let's have a string. So what's an easy way to get a long string? Pip install lorem text. I don't know if I can do that. Maybe. I ended up using my own environment, right? Let's see if it works. Disk quota exceeded. Oh, come on, not this again. All right, I don't get lorem text. I'll just do it myself. Where? Where can I find it? I want 2 paragraphs, please. Here we go. Whatever. Hey, it didn't work. Oh, here it is. Lorem ipsum. That's a bunch of words, right? I don't even know how to read it. So let's go lorem ipsum equals all those words. Words equals lorem ipsum dot split, right? And then how many are there? 247 words. So let's go workers equals joblib dot parallel n jobs equals 4 and tasks equals 4. Oops, I need a function. So let's define vowel checker, which takes an argument W, which is a string. I don't think that's going to work. Let's vowel checker and we'll do vowel count equals 0 for C in W if C in A, E, I, O, U, Y, A, E, I, O, U, Y, vowel count equals vowel plus equals 1, return vowel count. And then we need to transform that. So later function equals joblib.delayed of vowel checker. Is that how it's done? It's lowercase d. I think I want to put that in its own cell. So I can check it. Print later function. Okay, so there's a function. So for word in words, later function word for word in words. And let's make sure they're actually tasks. Yes, that is a task. So now we can do results equals workers tasks. Ah, I forgot to print the results. Yay! And now I think I know how many vowels are in the first 247 words of Lorem Ipsum. Thank you, Prasad, for this suggestion. Did anyone else have fun watching me struggle through that live without trying to embarrass myself too much? At this time, we are ready to proceed to learning the Dask module for parallelism in Python. Don't forget to import Dask. You definitely need to run the cell, and it will show you that you have Dask installed somewhere. I installed Dask in my training virtual environment. So, like Joblib, Dask provides a function named delayed. It works very similar. So if your original function looks like result equals my function with arguments, then you can call the delayed function by wrapping my function in dask.delayed. Then when you call it with arguments, instead of computing the function, it just remembers those arguments for later. So the result of a delayed function is an object, but it's a little more complex than a joblib task because the Dask delayed function knows that it's part of a graph. So we can use Dask visualize to inspect the graph. The next thing is the Dask graph will not compute its function calls until it needs to. This is called lazy. You can prompt execution by calling the compute method of a result object. So example 1. Here's a loop that computes the sum of the first 5 square numbers. So first we have 5 numbers. Then we square each of the numbers and append them to the list so that now we have the first 5 square numbers. Then we compute the sum of all of those square numbers. So the sum of the first 5 square numbers is 55. If you play Sudoku, never mind. That's not a Sudoku number. So the sum of the first 5 square numbers is 55. I feel like there's a fun fact there, but I forgot what it was. Sum of squares. There's got to be a fact there. It's a pyramidal number or something. Anyway, back to learning about Dask. So now we take this algorithm and we're going to just insert dask.delayed on the square operation. You'll notice that I defined a function square instead of just using x.x because you can't dask delayed x.x. It has to be a function. So I just wrapped x.x in the function square so that I can call dask delayed square. So now it's define square, define data, set dask a config number of workers. So now any graph can be executed with a number of workers. So instead of giving tasks to your workers are just always ready. Then we have our for loop that says for x in data, a equals dask.delayed square x output.append a. So now output will be a list of dask delayed functions, right? Then we can dask delay the sum. That's what's new, is now we're calling dask delay on a function and we're passing the input to be things that are already themselves delayed. So now we're twice delayed. So the output is a list of delayed tasks, but now we're going to delay the sum. So the total is what? A graph that teaches you how to compute the sum, but we haven't computed anything because we want to visualize the graph. So if we dask.visualize total, you now get an actual visual graph that says, I know that I need to compute the square, and then I need to take those results and I need to feed them to the sum. So that's really neat that we executed sum and square, but we didn't do any of the work. Dask took notes. Dask was taking notes and now it knows it needs to feed the information like this. Isn't that great? So now whenever you're ready to compute this graph, we just call its compute method. So total equals total.compute 55. So your exercise will be the same thing we did before, but now instead of Joblib, I would like you to use Dask. And instead of computing the max now, I would like you to compute the max later so that we can view the graph. What do you think about that? Does it seem fun? I see a suggestion in the chat, Fibonacci. The Fibonacci sequence is, I'm not certain you can parallelize the Fibonacci sequence. Can you? Can you parallelize that? Because Oh, 55 is a Fibonacci number. Yes, it is. I know that one. That's probably why I felt like it was special. Thank you, Sandra. Okay, so you weren't giving me a suggestion, you were helping me remember why I thought 55 was a special number. There's gotta be a theorem out there that says all the numbers are special, right? For every number, there must be some weird puzzle where it's the solution, right? Because there's probably infinitely many puzzles. Okay, what were, oh yes, it's exercise time. So I hope you are all paying attention and ready to use Dask to get the graph of how to compute the maximum number of letters in a word in a list of words. Does anybody have a solution you would like to share? So like with Joblib, I bet there's a nearly one-liner solution to this problem. Anybody want to dare for a nearly one-liner solution? String dot split lorem ipsum for word in string dot split lorem ipsum dask dot delayed length word for word in string dot split lorem ipsum as a list dask dot delayed max of that list and how do you visualize it? Dot visualize. No! What have I done? Oh, I did it wrong. You put lorem ipsum before the word split. Rookie mistake. Oh no! What have I done? Do you see what I've done? I'm so silly. There's 247 words in lorem ipsum, the variable. So the graph is there's 247 length calculations, and then they all feed into a max calculation. So when you plot it, it's absurd. Look at this. It just keeps going. What have I done? All right, so yes, there was a one-liner solution to this, and I found it. And yeah, method chains, right? Well, we love those method chain. Did you know you can drag this stuff around? I did not know. I accidentally dragged one and I was like, oh wow, you can do that. How fun. Um, yay. Did anybody else find a solution? Would you like to? I'm going to hit it with the compute now, if you don't mind. Instead of visualize, let's hit it with compute 12. Apparently, the greatest number of characters in a word in lorem ipsum was 12. I did not know that. I've never done the challenge before with lorem ipsum specifically. What is the 12-letter word in lorem ipsum? Consecutor? That's not 12. Must be a longer one in here somewhere. It's not vestibulum. Solicitudin. That's got to be it then. There you go. Solicitudin must be the longest word in the first two paragraphs of lorem ipsum. I am sharing my screen, right? And talking. I just had this weird feeling like maybe nobody can hear me. Could somebody please speak up in chat and say literally anything? I'm going crazy. Thank you, Aravallo. Okay, so did anyone have a question about using Dask delayed to assemble a graph and compute it? Would anyone like to propose a different activity? I suppose we might move on to a new parallel strategy. So far, we have one parallel strategy, which is how do you parallelize an embarrassingly parallel for loop? And now we should say, well, not everything is a for loop, Richard. What about vector processing? That's not a for loop. Correct. So let's talk about vector processing, which is doing arithmetic on arrays. So let's talk about parallel with arrays. So let's learn about NumPy arrays. Anybody seen NumPy arrays before? So a NumPy array is a data structure that has many of the same properties as a list, but it has an extra property that you can compute operations on the elements of an array by writing the operation on the array itself. So instead of for element in array, do element squared, you can just write array squared. And what that means is square each element of the array and return the array that is the result. So it's a very common way to express the concept of vector operations is using this notation, which comes from NumPy arrays. So if we have my array, we square the array, then we compute its sum. So we can use the sum function that's the Python built in, but it's better to use the NumPy sum method. So the 14 is the sum of the first three squares. So let's try to express a vector operation like this using Joblib. I mean, okay, you can do it, but you can't use NumPy's methods. You have to define your own functions because the delayed cannot wrap a method. It can only wrap a standalone function. So instead of using NumPy's sum method, like row.sum, we have to wrap NumPy sum around. We have to like steal NumPy's sum function, but we can't use row.sum. So this is squares.sum. We wanted to compute with the sum method, but we cannot. We have to wrap it. We have to go grab a regular function to do the job. So we create a vector operation. This vector operation is add 100 numbers. So wait, what is, no, is it rows, columns, right? So it's add 100 numbers and do that 10,000 times. I think that's what that is. So then it's, we will be computing the sum of a row later for each row in the data. And then you have 4 workers. And so then you have, oh, that looks like a, yeah. So that's, wait, no, I said that. Did I confuse myself? For each, okay, so it's for each row, compute the column. So the sum, no, it's rows, columns. So add the sum of a row is all the columns added together. Sorry, the words, I get the words confuse me. It would be helpful if I could visualize this, but sadly, there's no way for me to visualize this using only Joblib and NumPy. So yeah, you can add together some numbers, but it was kind of awkward. Like, really? Wrapping NumPy sum in another function? Like that's not great. So can Dask do better? Yes, because Dask has an array submodule. So Dask.array is a module, and Dask array array is a class. Oh, because I forgot to import the module. Okay, you have to import the module before you use its class. So class Dask array is a wrapper around a NumPy array. So it knows how to use NumPy's methods. So you're getting NumPy methods, but you're able to delay them. Does that make sense? In fact, they're automatically delayed. Because what would be the point of having a Dask array if you weren't going to delay the methods? So a Dask array is the same as a NumPy array, except all the methods are delayed. So if you go, I want a Dask array of 1, 2, 3. Yep, it do be an array. Then you can do, let's have a Dask array of a lot of numbers. And here's a fun keyword argument, chunks. So we're not talking about chunks right now, but chunks are a generally relevant concept in vector arithmetic. You don't have to process the whole vector in memory all at once. You can load part of it into memory, do the computation, then unload that. And so you can process a vector that's larger than what fits in memory if you understand chunks. So I'm just showing the chunks here, but I'm not going to explain how they work right now. So what was I going to do? Yes. So a Dask array of random numbers, and then when you do data.sum, axis equals 1, so that's just a normal sum method. Axis equals 1 means you add columns together. So we're doing the same thing we did before, right? So add all the columns together so that each row just becomes a single number. But we're using a method. So data.sum is how you get the sum of within each row, but it's not going to compute. It's delayed. It's already delayed. Data.sum is numpy.sum, but delayed. So then you can call the compute method. And if you didn't specify a number of workers, then you can also specify a number of workers as a keyword argument. And so here's that. That is, well, it's not as many numbers as the other one because I changed it for some reason I can't remember. Maybe if I just put a 0 here. Yeah, okay, now it's the same. So now we can do 100 of get the sum of 10,000 numbers. And so each of these is on average half of 10,000 numbers. I got frazzled and I forgot what I was doing. What are we doing? Would you like to do an exercise? Does a visualization exist for the array? I do not know. That is an interesting question. What if we just ask? What if we just go like this? What was the function again? Dask.visualize. So dask.visualize data.sum. I don't know what's going to happen. It works. Fantastic. Who would like to help me interpret this graph I've never seen before? So it looks like it says we're going to generate a random number. We're going to do that 4 times. Each random sample is a different shape. And then No, maybe, what is that? I don't even know what that is. I think it's put it in a different position in the array. Generate 4 random numbers, put each one in the array, compute the sum of the 4 random. Maybe random sample is computing more than one number. Maybe it's computing like a large number of numbers. How many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So compute 10 random samples. And then compute the sum of each of the 10 random samples, and then compute the sum of the sums, and then compute the sum of the sums of the sums. Oh, I see what it's doing. Instead of computing all the sums, it's together, it's doing subtotal. So here's the subtotal of this chunk. Here's the subtotal of this chunk. Here's the subtotal of this chunk. So that you can load this chunk into memory, get the sum, and then unload this. Load this chunk into memory, get the sum, and then unload this. So it's being memory efficient. I think that's what it's showing us here. I think it's something like, well, you know what, maybe they are chunks. If each one of these is a chunk, then you load it, you get its sum, then you discard it. You load it, you get its sum, then you discard it. And then if there were 10 you know what? I bet that's what it is. I bet that's what it is. I bet each of the random samples is one chunk because there were 10 times as many data points as there were chunks. So there should be 10 chunks. So I bet that's what this is. I think it's make a chunk, it'll be an array, compute its sum, then we can unload that and do the next. But then we have 4 workers, right? So we probably load 4 chunks into memory at once, compute each of their sums, then unload all 4 of those, something like that. What do you think? I actually don't know. I only barely know how to use Dask. Thank you for a very excellent question from Trevor. Would anyone else like to suggest a question or an exercise relating to Dask? Perhaps we could visualize a different operation. What did we compute? We computed the sum of random numbers. Is there anything else we can do with an array? We could square the data. We can compute the sum of squares. That's interesting. Oh, but of course, then you have to put it in parentheses. Okay, so you compute the sum of squares, I decided. Yes, it's possible to compute the sum of squares. So we can visualize computing the sum of squares. Let's see where it puts the square operation into the graph. Aha! So now we compute a random sample, we square the random sample, then we sum the random sample. And we do that 10 times, and then we compute the partial sums, and then we compute the final sum. What if we then square the result of that and then compute its sum? Okay, so now it says do everything and then take the square and then sum it. Okay, so I think what it's saying is this box doesn't represent one number. This box represents an array of some shape. So these arrays were larger because they haven't been summed yet. And then after you sum them, they get smaller. And so by the time you get here, the array is not as big as it was before. But each box does not represent one number. Each box represents an array. So when we get to here, we're doing the squaring again, but this isn't square a number. This is square an array to make a new array. And that is kind of the power of expressing your vector arithmetic like this. If you can express vector arithmetic like this in code, then you should also be able to express vector arithmetic like that in a graph, where a node is a vector, and then the operation is meant to be to each element of the vector of the vector. So then you don't have to write the square operation 10,000 times in your graph. You just have to write it once for each time you want to perform it on a chunk. So it's like once per chunk or something like that. My goodness. I'm very distracted by this. What a fantastic question. Do you want to continue talking about Dask, or do you want to move on to the last topic of the day? We do have one more topic. It is not very long. We could just try to finish it and end. What do you think? No more questions about Dask right now? My brain is cooked. If I get another good question, I might just melt in my chair. Let's talk about checkpointing with Pickle. I could use a pickle right now. I am hungry. All right. Checkpointing with Pickle. What do we need to know? So the idea of checkpointing is there's kind of two things. One is you have to regularly, while you're working, stop and save and make a record of where you are in your work. And then if you get interrupted, before you start working, you check to see if there's a past record of your work. And if there is, then you start from there instead of from the beginning. That's kind of the tedious part, is setting up the logic of, have I been interrupted? If I have, figure out where I was and resume from there instead. That's kind of the tedious part. The part that's technical is, how do you actually save the state of a Python program? So Python objects exist in memory, but they're very weird. If you ever looked inside of a Python class, there's a lot of nonsense in there. So Python has some helper tools and to help you deal with it. So Pickle is probably the most easiest, like user-friendly of the libraries that will help you to do what is called serialization and deserialization. So serialization means we transform the objects in memory into a binary file. And then deserialization is the opposite. You transform that binary file back into objects in memory. So the state of your program is not just a list of the numbers that you would need to reconstruct the objects if you did it yourself, but it is actually the objects themselves. So even if you don't know all of the objects, but you know how to put them into a structure, you can pickle the whole structure, and you don't have to worry about the problem of, how do I figure out what that structure is going to look like when I want to resume my state? So it has like recursive complexity, solves the recursive complexity problem. Does that make sense? Where am I going with this? I'm going to the notebook. So we'll shut down this one. We don't need it right now. So I will stop this one. Okay, that's stopped. And we will start up the checkpointing notebook. Everybody excited to learn about checkpointing? Now, I don't exactly have a, what do you call it? An exercise. I don't exactly have an exercise prepared. It's more like a demo. But what I can do is I can challenge you to come up with your own exercise, if you want. If you don't want to, then I guess you can just say, thanks, have a good day. But no, hold on. Stick around for the demo, and then you'll decide. So first, we'll have Pickle And sorry, I didn't put this in the slides. It's an actual visualization. So the objects, but in Python, objects contain each other recursively. So like a list contains elements and elements contain their methods, and the methods contain references to functions that are in libraries. It's very complex. So you don't want to worry about that recursive complexity. So serialization and deserialization is there an easy way to do it? The answer is Pickle is easy mode. So you import Pickle, you print Pickle. So Pickle comes from somewhere. In this case, it came from here. So Pickle didn't come from my virtual environment. You can see it came from the base Python, Python 3.11. It's one of the base modules that's available with Python. So Pickle has a dump function. So pickle.dump writes data to a file. What kind of data? Literally almost any Python object. So here's a dictionary. A dictionary is a valid Python object, and it has recursive complexity because it contains strings and integers, and strings and integers have methods, so they're complex in and of themselves. So we have this data object, and you can say, I'm going to have a file. This is just the normal write to a file in Python. There's nothing special about the file. The point is that it's just any kind of file, and then pickle.dump is what actually puts data in the file. So we write the data to the file. Now how do we undo that? From OS import name. I don't remember why that's there. That might be a typo. Then we do with open data.pickle. I think this might be a typo. So with open data.pickle as file. So it's just a regular file. And then you do pickle.load, and that returns something. What is it? Let's print its type and see what it is. It says it's a dictionary, and here's its elements. Well, that's the same dictionary we had before. So Pickle successfully moved a full Python object with all of its recursive complexity through a file handle, brought it back, and recovered a full Python object with all its complexity. That's so easy. No wonder people like pickles. They're easy, but they're not secure, by the way. If you find a pickle on the internet, it's basically you should treat it like a virus or something. Pickles can contain arbitrary code execution because they have the full complexity of Python. So loading a pickle is kind of like executing a Python program. So it's fine to have pickles that you just have for yourself, like intermediate steps for your program, but you should not be sharing pickles over the internet. These are not safe. That's the downside of Pickle. If you want a safe checkpoint, you have to use something other than Pickle. So for example, there are many domain-specific checkpoint formats. Have you heard of the safe tensors format that is used for sharing the weights of large language models on Hugging Face? Have you heard of this one? I've heard of this one because I'm interested in machine learning. So if you go to Hugging Face and snoop around, you will find that there are a number of files that you're available to download that are in the safe tensors format. And essentially, safe tensors is doing what Pickle does, but in a much more restricted way. It is only allowed to save model weights and load model weights. It is not allowed to do arbitrary code execution. So that domain-specific restriction of it only does the one thing makes it safe for sharing. Whereas Pickle does not have any restrictions. It can do anything. It can do arbitrary code execution. So hopefully you're understanding the point of me telling you this disclaimer. So now that we know how to move the state to a file and back again, we had to construct an interruptible task, which is kind of the tedious part. So the task that I'm doing is a Fibonacci sequence because Fibonacci sequence is stateful. In order to compute the Fibonacci number, you need to know the previous two Fibonacci numbers, which means that the state of the program at any time is essentially two Fibonacci numbers, the previous two that you computed. And if you do not know both of them, you do not know your state. So whenever you are doing an interruptible task, the first thing you should do is check to see if you previously have already been working on this task. So let's say there's a Pickle file and we check if it exists. And if it does exist, then sorry, if it doesn't exist, we create one. So the initial state of the Fibonacci sequence, if you don't have one, is that your first two Fibonacci numbers are 0 and 1. You can also start from, 1 and 1. So you start from a pair of ones. So the 0th Fibonacci number is 1, and the first Fibonacci number is also 1. Are you with me so far? Now, you only create the starting state if you didn't have one. If we do have a starting state, we skip that and we go to loading. So we load the file. We get the state out of the file, and we're going to assume that the state is a dictionary with this structure. So it has a previous Fibonacci number with an index and a value. And it has a last Fibonacci number with an index and a value. So now that we have a state, we either create a fresh one or we load one from disk. We now do the infinite loop. So I'm using time.sleep to slow it down because I don't want to jump all the way up into the millions immediately. I want to be able to see the Fibonacci numbers go by. So sleep for 2 seconds and then compute the next Fibonacci number and then add one to the index. And then we'll display them. And then we will compute the new state. So the new state is you shift the last one over into the previous one, and then the last one is what you just computed. So the index and the value you just computed. And then you save your state, because after you've done some work, you always save your state. So let's view that. So if we initialize the state 0, 1, 1, 1, 1, 2, 2, 3, 3, 5. I think I got my print statement wrong. Yeah, something's not right with my print statement. Whoopsies. But it's computing Fibonacci numbers. Every 2 seconds, it computes a Fibonacci number. Now what happens if we stop execution? We interrupted it with a keyboard interrupt. In fact, let's go even further. Let's kill the entire Slurm job. Abort with prejudice. You're gone. Now I need to start a whole new job from scratch. I woke up in the morning, my job's dead. Oh man, that's life. So queue up a new job. Get back into your notebook. Import your module. All right, let's start the Fibonacci over again. Okay, so the first Fibonacci number is 89. The second Fibonacci number is 144. Wait a minute. That's not right. Well, it's what I wanted. The Fibonacci sequence has resumed from where I left off, because instead of initializing the state, it read the state out of the file, because after every work step, we save the state. So your exercise, should you choose to accept it, is inspired by what I have done. Now, you don't have to have your state be Fibonacci numbers. The reason I have a next and a last is because I'm doing the Fibonacci sequence. You can do any stateful task. That is, in order to do work, you need to have the previous work you did. So another example would be squaring a matrix. Anybody know how to multiply a matrix? If you want to square a matrix repeatedly, then it's stateful because multiply two matrices repeatedly, then you have to have the previous matrix in order to continue multiplying. So that would be a stateful operation. Or text generation is stateful, because if you're generating one token at a time and your job stops, you want all the tokens you already generated, then you can continue generating the next one token at a time. So large language models are an excellent candidate for checkpointing, and in fact, they have that, and it's called it's called a context cache hit. If you sign up with a provider that has context caching, what that means is they save the token representation of your input for a while, so that if you decide to continue generating input, they can skip the initialization steps and go directly to continuing generating input from where you last were. And that saves you money if you're doing tasks that build on themselves. So an example of a task that builds on itself is like tool using. You use a tool, you get the result, and then you continue thinking. Then you use a tool, and so the essentially tool use is a large language model being interrupted because it is no longer able to think. It has to wait until that tool tells it the answer to the question. But the GPUs shouldn't be sitting idle, so they put the context aside and they work on someone else's query for a while. And eventually the tool response comes back, and then they can swap your context and the tool result back into memory and keep going. So checkpointing is an absolutely key feature of efficiently doing large language models at scale. And I am pretty much out of words to say about that. So would anyone like to suggest an exercise for checkpointing that we can do in a few minutes before my brain completely shuts down for the day? Or do you have a question that you would like to ask about checkpointing or any other hobby of mine that you find interesting? So if we look at the files, I'm curious. We know that Pickle file is somewhere, right? Wonder if I can find it. So I go to the training directory. Aha, look, there's a state.pickle file. So that's new because my notebook created this. So I can't open it. It's not a text file. If you try to view it, it's like, no, I'm not even going to try to view it. You can download it. It's a binary file. I don't know how to interpret what's in there, which is why when I'm building applications that need to be stateful, I don't use Pickle. I use human readable formats like JSON. If you're saving objects like dictionaries with strings, dictionaries and strings can be represented in a human readable text form. It's not space efficient, but you can read it and inspect the state. So JSON is a human readable way to save reasonably simple structures like this. I can show you the same code, but instead of Pickle, I'll use JSON. Are you interested in that? So instead of Pickle, let's import JSON, and we'll have the output, the state file be state.json. And then instead of pickle.load, it'll be json.load. And instead of pickle.dump, it'll be json.dump. So basically a one-for-one swap. So you initialize the state, and then you immediately get an error. json.dump state file. I think it's because I put the arguments in the wrong order. JSON dump data file indent. Oh, I needed to change the writing mode. It's not a binary file. It's a text file. So I delete the B's. because JSON is text files. And now I have a broken file. I'm going to, yeah, it's empty, so I delete it because I can't use a broken file. Okay, so initializing state, and then we compute Fibonacci numbers. But now, instead of Pickle, I'm using JSON. JSON. So we can stop this, and we can inspect state.json. So I'll just use my file navigator, view, but state.json is just a plain text file. So you can view it's all text. It even looks pretty similar to Python. Not exactly identical to Python, but very similar to Python. So, so you can inspect it. And that's good if your checkpoints are not very large. If they're small, it's better to use JSON. And then we can resume, and it reads the numbers back in and continues calculating Fibonacci numbers. So, if you're dealing with numbers that are just like simple numbers, and there's not very many of them, JSON gives you the advantage that your checkpoints are human readable. If you're dealing with something complex that's not numbers, weird Python objects that can't be expressed with just text, then you would use Pickle. And Pickle is more space efficient because it's a binary file, and it also can do a wider variety of object types, like arbitrary Python types, but it's not human readable. Did anybody want to say anything? I'm pretty much out of stuff to say. So if nobody wants to say anything, then I will go to the acknowledgements slide. This work was supported by the National Science Foundation. So we have some award numbers. We have the ACES award, which paid for the wonderful computing cluster that we used for our exercises. The Sweeter award, which paid for some of our time to develop the materials, and faster because I can't remember why. Yeah, because some of what I learned about containers, remember we used containers earlier? A lot of what I learned about containers, I learned by working with the faster cluster. And I would like to thank the staff and students at A&M. We've had several today who helped us with dealing with tech problems and also with managing the Zoom session. I would not be able to run a short course by myself. I would like to thank the ACES CSET pilot program because I forgot why. I don't think they paid for this one. I think that's a misplaced acknowledgement. Sorry about that. And we have a short course survey, which is this QR code. The QR code is the same as the link. I'll drop in the link in the chat. Someone is asking about Zoom recording. We do record our short courses and we put them on YouTube, and it takes like a week for us to do that because we have to process the video and make sure it has captions for accessibility, and the video processing is not fast. So usually in like a week or something, we have a YouTube video of today's what are we doing? A short course? So anyways, the short course survey, we ask you questions about what you found helpful, what you would like to see more of in the future, so that we can tailor our catalog of courses to meet your needs. Not as an individual, as a community, we would like to meet the needs of the community, so we need to know what you need. So please respond to our short course to let us know if we're doing well, how we can do better, and then we want to read those. So it's very important. So please do the survey. And that is the last. No, it's not. The last. Yeah, it was the last slide. I had a backup lunch break slide in case the lunch break slide was broken, but I didn't need it. The lunch break slide was fine. So I'm just going to shut down my notebooks because it's you turn the lights off when you leave the room, right? Just be considerate to others. So I'm going to my jobs and it stopped. Why did it stop? I can't remember. I think it was because I shut down a notebook. Did I? Can't quite remember. Maybe I did. Where am I going with this? I'm not going anywhere with this because I'm losing my mind. So after a long day of teaching, my brain doesn't work so well, and I start sounding like nonsense, which is why it's important to know when to give up when you're ahead, right? Something like that.